View of the optimization exercise we did in class yesterday. And to start with, we'll do question 1, the compiler optimization that moves computations out of a loop when the computation would produce the same results every time it's executed is known as code motion. This next one here is a little bit poorly worded. The compiler optimization that multiplies the size of the loop body by some unroll factor is known as loop unrolling. Multiply the size of the loop body is not very accurate, so I put a different question down, number 7, which does a better job of explaining that. The optimization that reduces the iterations of a loop by including computation of more than one result per iteration is called loop unrolling. That's a better way to describe loop unrolling. So look at question 7. Number 3, the compiler optimization that replaces a more expensive computation with a less expensive one in terms of cycles is called strength reduction or reduction in strength. I'm not sure that we covered that in section 101 at 8:30, but that's a common form of compiler optimization where we're essentially trying to replace more expensive operations with less expensive ones. I give an example over here, for example, replacing multiplication with a shift left in this case, or division with a shift right if you can divide by a power of 2. And sometimes you can convert a multiplication to an addition, and I'll show an example of that in the last problem. That's called strength reduction. The next optimization, the compiler optimization that avoids repeated computation of the same expression in a block, is called common subexpression elimination. Another abbreviation for that is CSE, so you could put CSE down there. Common subexpression elimination. And common subexpression elimination, a lot of times this can occur when you're dealing with matrix or array, particularly higher dimensional arrays, where you have expressions to determine what index you're dealing with. So, for example, over here in my comment, I've got an I plus j minus 1 and an I plus j plus 1 as expressions to evaluate an array index. The I plus j might be constant within a particular block of code, and so that might be calculated once, and then we use a substitution temporary to store that. So that's an example of a subexpression, and we try to eliminate common subexpressions by calculating them once. That's called CSE, or common subexpression elimination. A compiler will not typically attempt to optimize a function call because it might have side effects. This is again a not very well worded question. This is from an old exercise. I should have reworded that. A compiler will not typically attempt to optimize a function call out of a loop using code motion because it might have side effects. So the context here would be we're taking a function call out of a loop, for example. That's the typical application of this, and if you can do that, the programmer themselves should take care of doing that because the compiler won't do it. A compiler will not attempt to optimize code which involves accessing memory using 2 or more pointers because of a problem known as memory aliasing. Okay, 7, we just talked about that one a second ago. Here's one that we introduced yesterday when we were talking about processor level or machine level optimizations. An optimization that breaks a sequential dependency in pipelined functional units, allowing higher throughput, is called a reassociation transformation. If you remember the example where we reassociated a multiplication so that the scheduler, the superscalar instruction control unit, could actually schedule parallel multiplications that were not dependent on each other just by changing the location of parentheses, reassociating. Okay, so that's the reassociation transformation. And now we look at some compiler optimizations, and we look at, in this case, we look at an unoptimized snippet of code on the left and an optimized version on the right, and we ask the question, would the compiler do the optimization? Notice that the optimized code on the right is really a representation of what the assembly would be. So in the first one here, we see that we've got a sum is equal to sum plus a sub I plus get z. I is changing in this loop. Get z seems to be a constant function. but the compiler won't optimize that because getZ, this optimization here, it doesn't know whether getZ has any side effects. So that's the explanation there. For the next one, we look at it and see, okay, we have a sum. We have a sub I plus b times n, where n seems to be, n is a constant inside this block here. And we notice that we factored out the b times n using code motion into a temporary, and we're going to now use the temporary inside the loop. Would the compiler do this? And the answer is yes. There's no problem with side effects. There's no problem with aliasing. So it would do this. Third one. Now we're going to look at an inner loop that's got an array being accessed read, a sub I is being read, star b is being read, and in this case a sub I is being written to as well within the loop. So since a and b are both pointers, the compiler would not try to take out the star b times n. The idea being that star b times n might be a constant. But if star b accesses an element inside the array because they're overlapped, then we have this aliasing problem. So the compiler would not do that. Alright, so the answer is no. Memory aliasing is possible. A and B might overlap. So number 4, if you look at this one, we see once again we have two arrays, star A and star B pointers, and we see a calculation here. But in this case we see that we're going to factor out the star B times n into, using code motion, into a temporary, and then we use the temporary inside the loop. Can we do this? And the answer in this case is yes, because a sub I and star b are both being read, but you'll notice that neither of them is being written in the course of the loop calculation. So in this case, aliasing would not be a problem. Alright, so in the next problem we have some C code here and a unoptimized and an optimized version of the assembly code. You'll notice we have a star sum equals 0 using a pointer we're being passed. We update the sum by essentially adding up the elements of an array where the array has a dimension n, and so we're looking at the unoptimized and optimized versions of this code in assembly language. Now, the first question is, in both versions of the assembly code above, circle and label all references to star sum. In other words, accessing the value of sum itself at, using the pointer sum. So what we want to do is find out what that is. Well, sum, if you remember, is going to be using a particular register. RDI is going to be used for array, RSI is going to be used for n, and RDX is going to be used for the pointer sum. So if we look at our code over here, we come down, we notice that RDX is saved in a particular location on the stack. Notice we're using the frame pointer in this case to set up a stack frame, and that value is being passed into RAX, so it's the pointer is being saved in RAX, and we notice that right here we have an access to the value at the address stored in RAX. So this is an access to star sum. Likewise, if we look in this loop, we see RAX being used again here, and we see it being used again down below. In each case, we are accessing the value at sum. So star sum is being accessed. In the optimized version, once again, same is true, but now we see that RDX is being used directly to be initialized, and that's star sum. And we see another version of RDX down below, and that's also star sum. So these are the places that star sum are being referenced. Okay, and I circled in blue here this chunk of code because this is the main loop, and we're going to look at that a little closer. So it says rewrite in the number 2, rewrite the C code above, put your answer to the right of it to show how you would optimize it by hand, assuming that it is called this way. Notice that the way it is called is we've got a total, which is a variable, and we're passing it an array and an n and the address of total. Now notice that array and total do not overlap, and so since we know they don't overlap, aliasing is not a problem. If we were to optimize this by hand, how would we do it? Well, the answer to that would be we would set up a temporary, we would initialize it to 0, and we would accumulate our result in a temporary, and then write that temporary out to star sum at the end after the loop is complete. So this is the best way to optimize it. You only do one write to star sum, and this allows the compiler to accumulate the result inside of a temporary, which is going to be a register, or typically will be a register. Now the last question in this part here says, did the compiler optimize the code the same way that you did? How did the compiler optimize the code? Well, I'm assuming that you did it this way that I just showed you up here. Well, how does the compiler optimize it? Well, look at the inner loop. In the inner loop, we're grabbing an element from the array into RCX. We're adding that element to star sum. So we're actually accessing star sum. We're adding the elements, and then we're writing it back. And then, so we're actually doing the memory access in this case. We're not simply updating a temporary variable in a register. So in this case, the compiler is not doing it the way we would do it. It is accessing it on every iteration. So, and it's accessing it as both a read and a write. Since we're doing an add instruction, it's reading what's stored at RDX, adding it to RCX, and then writing it out. Okay. So the compiler retained the updates of star sum within the loop because of the potential memory aliasing between the array and sum. Now it's possible that you could use a hybrid approach. If the compiler had a higher level of optimization, it might accumulate in a temporary and then only do writes to RDX indirectly, so that it would just do a move after accumulating. That would avoid the additional read from RDX each time around. So the last problem, how might you apply code motion to optimize the following nested loop? Well, code motion is going to be looking for loop invariant expressions somewhere, usually inside the most nested part of a loop, or it could be anywhere though. So we're looking at a doubly nested loop. I goes from 0 to n minus 1, j goes from 0 to m minus 1, and inside here we have some expressions to assign to a two-dimensional array. Now x is not changing throughout the innermost loop, so x times x looks like a loop invariant. 10 times I is invariant with respect to this innermost loop because I doesn't change inside the innermost for loop. And then 100 times j, this is changing inside the innermost loop. So one solution that you could apply to this is to say, well, let's let temp1 be x times x, and once we do that, we can let temp2 be 10 times I, since I is changing only on the outermost loop. Let's factor 10 times I out of the inner loop, and we'll say 10 times I plus temp1. So that gives me 10 times I plus x times x outside of that innermost loop. That's what this line here is. And then after that, inside, now we have that assigned to temp2, and now temp2 is simply incremented by 100 times j. So we have, since 100j is dependent on j, we leave that inside. So that's one solution. A further optimization can take place because we could use what's called a reduction in strength. And a reduction in strength uses substitutes a less expensive operation for a more expensive operation. So notice that we've got multiplications here, but if we look at these carefully, we'll see that the 100 times j, since j is just changing from 0 up to m minus 1, it's incrementing by 1 every time. The compiler can actually look at that and change the multiplication of 100 times j on each iteration to a simple addition of 100. Likewise, you'll see that the 10 times I is dependent on I. These expressions here, 10 times I, which depends only on the index I within this loop, these are called induction variables. And you can change that from multiplication to an addition. And so if you look at this further optimization down below, what we've done here is said, well, let's let temp1 equal to x times x as before, but now I'm going to factor out the temp2, and I'm going to say let temp2 equal to temp1 on the first iteration. Now that makes sense because I at first is going to be 0, and so temp2 would be equal to temp1. Notice that what we'll do then is we'll let temp1 increase by 10 every time, which is exactly what happens. On the next time around, I is going to be 1, and so temp1 plus 10 is going to go to temp2. So that's what we do on this outermost loop. We increase temp1 by 10, and then we assign it to temp2. In the innermost loop, we will now update as we did before, but now instead of 100 times j, we simply let temp2 be incremented by 100, and we assign that to ij. So by doing this, we've substituted addition for multiplication, and this is an application of reduction in strength. It might also help us out with parallelism, since there are more add units in a superscalar processor, for example in the Intel processors, than there are multiply units. And that's about it for this quiz.